Prabanjan.
Yeah, I guess it started seeing the screen.
Okay.
Good evening, everyone, and welcome back to the fourth day of our Astronomy Week. Today, we are glad to be joined by Apoorva Shah. She is an alumna of our college and she completed her BAc major in physics in 2019. She is pursuing her MSc from the University of Bonn in Germany. When she was still in college, she was an active member of Astro Club and was our senior. So we are very fortunate to have you here today, Apoorvadi, and thank you so much for coming.
Thank you so much for having me here. I'm pretty excited to be here today on this online lecture on the cosmological models of the universe. Today is May the 4th, a pretty special day. My name is Apoorva Shah, and I'm a master's student at the University of Bonn. And I was a student at the Ferguson College, and I graduated in 2019. So let's begin with the talk. The talk will proceed somewhat like this. We will cover different topics as they come by. So let's begin with that. Let's talk about some of the early ideas that existed about the whole structure of our universe. So, early on, people believed that we were in a static universe that was unchanging, and every galaxy was like in a particular point in space, and it always stayed there in that point in space. But it was also known that by means of gravitational attraction, these bodies should not stay where they are. So instead, we should have had a pretty unstable universe. So when Einstein came around and presented his field equations through general relativity, we had these. I hope you can see my cursor here. So you can see that these were the field equations that Einstein presented. And initially, these did not contain the factor lambda here. And when the scientist called Lemaitre tried to solve these field equations for the universe, he found that it should have a non-static solution. That is, you should either have like an expanding universe or a contracting universe, but you cannot have a static universe. So Einstein initially was not very happy with this idea of a dynamic universe. So to sort of compensate for this dynamicity, he tried to add this factor lambda here, which is commonly known as the cosmological constant. All he wanted to do was to make sure that we can explain the universe in a complete static way. But then Hubble came around and he found through redshifting of galaxies that the universe is actually expanding. He found that the further the galaxy was, the faster it was moving away from us, which only had one explanation, is that the universe was expanding. And now that the universe was expanding, Einstein had to remove this lambda factor from his field equations. And it's also known that Einstein called it the biggest mistake of his life. But turns out that this lambda factor, the cosmological constant, is not so useless after all. And it's pretty useful in theories today that try to explain dark energy. And we shall see in subsequent slides how we can use this factor of lambda to explain what dark energy is. Now that we know that the universe is expanding, we also know that the universe is actually accelerating. So there was this huge project called the Supernova Cosmology Project, which actually found that the universe is accelerating. And we also need to incorporate that when we're trying to make a model for our universe. So let's see. This was the very popular plot that Hubble made. And during Hubble's time, he could only make measurements up to a few megaparsecs. And you can see here that each of these dots are a galaxy. And the farther away the galaxy is, the faster it is moving away from us. So this was the plot that actually proved to us that the universe is actually expanding. Now let's try to make a comprehensive theory of how a universe should look like. And when we try to do that, we start with something called as the first principles. So the first principles when it comes to cosmology are these called the cosmological principles. And these are the two main points here are homogeneity and isotropy. So when you say that the universe is homogeneous, you say that in any point in space, if you were to stand at any point in the universe, say on Earth or on Sun or on a different galaxy, when you look around, the universe should always look the same to you. At any point in the universe, everything's going to look the same. Then you try to explain isotropy. You say that in every different direction you look, the universe has no preferred direction. In every direction, the universe looks the same. Now, I hope that you can differentiate between these two concepts. These two concepts are not the same, they're different. And then we have the very famous Hubble's law, which explains to us that the universe is expanding. Now that the universe is expanding, we shall use something called as expanding coordinates. Now that we know that the universe, as the universe expands, the lengths go on increasing. So to explain how these lengths increase, we shall use something called a scale factor, which is given here as A of t. Now the scale factor A of t tells you how a length r naught will change over a course of time t. So if I want to find out what change in a length r naught will be after a time t, all I need to do is multiply the scale factor to r naught and I will get the resultant length. These are often also called as co-moving coordinates. And in cosmology, all results that you need to use, you can find by using your usual equations, but just writing them in terms of these co-moving coordinates. All you're doing is changing your regular Cartesian coordinates to an expanding set of coordinates. Then we have Hubble's law, which says that the velocity is equal to h of t times r, where h here is the very popular Hubble constant. Now I shall make note of the fact here that h of t is a dot by a, and it changes with time. It's not exactly a constant, which is why in cosmology you often call this as the Hubble parameter and not the Hubble constant. It's called the Hubble constant because it varies very slowly with time, and for all practical purposes, you could always assume the value of Hubble parameter as the present value. So the value of the Hubble parameter is the Hubble constant, and henceforth I shall refer to this as the Hubble parameter. Then, because the redshifting of these galaxies is pretty important, we also have a relation between the redshift and the scale factor of the universe, which is 1 plus z equals 1 over a of t. And this redshift here is caused due to the expansion of the universe. Now you can see here that as you can consider this as the entire universe, and as the universe is expanding, these particular yellow dots here, they're remaining on their positions, but the space between them is actually increasing. And because of this, there's a redshift induced, and this redshift can be explained with this expression here. So one thing I have forgotten to mention is most of these results that I will be presenting today were initially derived using general relativity, but I will not assume knowledge of general relativity for the purposes of this talk. I shall try to explain everything using Newtonian mechanics. So let's go on. Now here I have a picture of the 2DF Galaxy Redshift Survey, which was done a long time ago. Today we have more data, but you can see here that each of these dots is a galaxy, and they are pretty uniformly spread out. So this shows us that homogeneity is a pretty good assumption, and we can use this assumption while we're trying to develop our equations. Now let's take our Newtonian universe. Let's say that you have a universe here which is spherical, and you have a total mass m inside, which is distributed uniformly in a density rho. And let's say that the initial radius of the sphere is r. Now we have a particle of mass m on the edge of this universe, and we're trying to calculate what the energy of this particle m is. So the energy of this particle m is just half times mv square, that is the kinetic energy, and minus gmm by r, which is due to gravitational potential, due to the potential created by the mass inside the sphere. Sorry. Now all you do is express this equation in terms of a comoving set of coordinates or an expanding set of coordinates. So you change the velocity v and the radius r, and you write it in terms of the comoving coordinates. Now, when you do that and you make the assumption that this particular factor here, 2e by ma square r naught square, is equal to minus k by a square, then you end up with an equation like this. Now, this is a very popular equation called as the Friedmann equation, and you might wonder what this factor k over here is. Now, this k factor is called the curvature parameter, and if you try to look at it from a Newtonian point of view, it will not make much sense. It will just look like another constant. But when you try to derive results through general relativity, this curvature parameter k actually tells you about the geometry of the universe that you're considering. So this shows you what kind of a curvature the universe you're considering actually has. Now, if you have some background in special relativity, you will know something called as the line element. And the line element in this case here is given by this expression, where the sk square actually gives you what the geometry of space is. And now you don't need to pay much attention to what this line element here is, which is popularly called as the FLRW metric. And I've only mentioned it for the sake of completeness. And if you don't understand it, you can completely ignore it. So now let's go on. Here we have the Friedmann equation that we just derived, where 8 square is equal to a dot over a square, 8 pi g rho by 3 minus k by a square. Now let's discuss a little bit about how this parameter k actually affects this equation. So this parameter k can only have 3 possibilities, that is 0, minus 1, and 1. So what this does is express 3 different possibilities for geometry. When you consider homogeneity and isotropy, you can only have 3 different possibilities when it comes to the geometry of the universe. You can either have a spherical or like a closed form of a universe. You can have like a hyperboloid kind of a universe with a negative curvature, or you can have a flat universe with no curvature. So for k is equal to 0, we have a flat universe. For k equals plus 1, we have a spherical kind of a closed universe. And for k equals minus 1, we have a negatively curved universe. And these results only, these interpretations only make sense if you look at it from the point of view as general relativity. Also, an important thing is that henceforth in all equations, I shall be using c equals 1, which makes all these equations look much cleaner and much easier to use. Now that we've found the Friedmann equation, we will also need some more machinery till we can actually move on to using this Friedmann equation to develop our model for the universe. We will need something called as the conservation equation. From the first law of thermodynamics, you know that dE is equal to P dV, where P is the pressure and V is the volume. You do the same old trick and you try to express this in terms of the comoving coordinates. You try to express this in terms of the scale factor. And when you try to do that and you use the fact that E is equal to M, and you get a relation for rho dot, that is, you get a relation for the time derivative of the density, and this is called as the conservation equation. Now, when you combine the conservation equation and the Friedmann equation, you end up with something called as the acceleration equation, which tells you how the second derivative of your scale factor is changing. So now here you can see that this equation here has a negative sign here. And for a universe that you want to be positively accelerating, you will need to have a double dot greater than 0. Only in that case, you will have a positively accelerating universe. And for that, you need this particular value here to be less than 0. Now, this usually does not happen because let's say if you consider that the density is a positive value, then you would require that the pressure definitely should be a negative value. And it's a little weird to imagine what kind of substances could have a negative pressure. So since we do not know what kind of uh, components can cause a pressure like that, we just call it dark energy. So to explain how the universe is actually accelerating is not a fully understood question. And as of now, anything that can make the universe expand like that in an accelerated fashion, we shall call that entity as dark energy. Now we have seen that we have these three equations, which are popularly called as the Friedmann equations. So here you can see that you have three main variables here. One is the scale factor A, one of them is the density rho, and the pressure P. But you can notice that there are only two independent equations and three variables, because the third equation here has only been found by a combination of these two, so it's not independent. So to find what these variables are, you need another equation. Because there are three variables, you need three equations. So for that, we shall assume an equation of state, where we try to make a relationship between the pressure and the density. Now we're trying to insert a dimensionless parameter called W, and this W changes according to components. So for just matter, W is equal to 0, and for radiation, W is. Now another important point I want to make here is that whenever I say matter, I mean regular matter and dark matter both, or anything that can exert gravitational effects for that matter. And a particularly interesting case here is when W is equal to -1. So in that case, P will be equal to minus rho. And that particular case corresponds to the cosmological constant that we talked about before. This is the same lambda that Einstein tried to call the biggest mistake of his life. But now we shall use it as our model for dark energy. So so for any models that I've considered in this talk, in the subsequent slides, I have considered lambda as a model for dark energy. And from the previous expression that we had over here, you can see that rho plus 3p should be less than 0. For any dark energy model, W necessarily has to be less than 1/3. So now that we have all the machinery we need for developing models, let's go on to, before that, excuse me. So now that you have all your equations, you can define some important parameters that are very useful in cosmology. One of them is called the critical density, which is just 3h squared by 8 pi g. Now the critical density is the density you would expect for a flat universe for k equals 0. And you also define a parameter called omega, which is just the actual density divided by the critical density. So if you measure this parameter omega and it's equal to 1, that's how you know that your universe is flat. Now the age of the universe can be calculated using this expression here. You can see that it depends on the Hubble parameter and the horizon distance. The horizon distance is nothing but the distance, the farthest distance up to which you can look. Now, because the speed of light is constant and the age of the universe is a finite number, you cannot look infinitely out into the universe. There is a particular distance up to which you can look. So this horizon distance is given by this expression here, and you can see that this also depends on the Hubble parameter. Now we try to make simple models of our universe, and these are just toy models that we consider to just see how well we can work with our equation. So let's take the case of a flat universe. We take k is equal to 0 in our Friedmann equation, and we take a single component. Now let's say that we have a universe with only matter in it and nothing else, just matter. So for matter, the density would go as 1/a cube, because as the universe expands, the radius increases as one power of the scale factor, and the volume will increase as 3 powers of the scale factor. So the density will decrease as 1 over a cube. And when you use this in the Friedman equation, you will end up with the scale factor going as t to the power 2/3. Now this is shown here in blue in this plot. Then you consider a flat universe with only radiation in it and nothing else. But when it comes to radiation, the density actually goes as 1 over a to the power 4th, because as the volume is increasing as 3 times of the scale factor, you will have to add another factor of scale factor, because the wavelength is also getting stretched as the universe is expanding. So in this case, when you use this rho of 1 over a to the power 4th in the Friedman equation, you will end up with a scale factor increasing as t to the power half, which is shown here in this case in orange. Now you can see in both these cases, the universe first starts expanding and it slowly starts decelerating in its expansion. And you can see that in both these cases, it starts from 0, 0. At t is equal to 0, the scale factor is also 0. That means there was a big bang here, after which the universe started expanding, but it decelerated in its expansion. Now let's take a case where you only have a lambda component in this universe. Now for a lambda component, you would have a density which is constant, which does not change as the universe is expanding. All it does is help the universe expand. So in that particular case where rho is taken as a constant, you would have a scale factor which goes exponential, and you see that the universe something like this acceleration is, and it's accelerating. The expansion is constantly increasing. Now, how do we compare this to check how correct our results are and if they match with experimental results? So for that, what we will do is we will try to calculate the age of the universe in all these different cases. So for a matter-only universe, you can see that the age is somewhat in the range of 9.5 gigayears. For a radiation-only universe, you would have an age of about 6.5 or 7 gigayears. But you can see here, as I've pointed out, we have found globular clusters which are older than 12 gigayears. And you cannot have objects in the universe that are older than the universe itself. So that's how we know that matter-only or radiation-only universes are not the right explanation here. There's something more. Now you can ask me one question here, is that why have I not included the lambda-only universe in this plot? That's because here you can see that lambda-only universe has a particular scale factor value at t is equal to 0, and there is no point at which it exactly hits the time axis. So that's why there is no situation of a Big Bang here, and because there is no case of a Big Bang, you cannot have an age for the universe. So the age of the universe in this case is infinite. Now that we know that none of these single component universes are explaining the universe well, let's take the case of a multiple component universe. And let's say that the universe is a mixture of 2 different or 3 different things. Now let's take an example where we have lambda and we have a non-zero curvature. So we're not taking k is equal to 0, we're taking a particular value of curvature, and we have the lambda in the universe. So for these 2 different cases where the curvature is negative and the curvature is positive, you have 2 different kinds of evolution for the scale factor. Here you can see that for the positive curvature, there is no Big Bang here, and it expands and it accelerates in its expansion. And for a negatively curved universe, you will have a Big Bang situation over here, and then it will expand. Now we can do this for different combinations. You can take matter plus radiation, you can take radiation plus lambda, you can take lambda plus matter, and you can try these different combinations and try to work them out using the Friedman equations. But a particularly interesting case is where you take matter plus lambda. And for a matter plus lambda universe which is flat, you have a scale factor which is increasing as sine hyperbolic to the power 2 to the thirds. So in this case, you can see that the universe has a well-defined Big Bang, which is good, and it initially starts expanding, it decelerates in its expansion, and then there's an inflection point. After this inflection point, the universe starts accelerating. Now, this is a pretty good uh, model to explain our current universe, and this led to the formation of something called as the lambda CDM model of the universe. Now, this lambda CDM model of the universe is considered as the standard model of our universe in cosmology. In this case, we consider that there is an initial radiation dominated era up to a redshift of over 3000. Then there is a period of matter domination. And until there is a period of radiation and matter domination, the universe decelerates in its expansion. But as the universe expands and the density of radiation and matter reduces, the lambda component of the universe starts taking over, and this lambda causes the universe to accelerate. Now, this can explain why our universe currently is accelerating. And another thing is, why do we call it cold dark matter? It's because as because for that, I will first explain what peculiar velocities are. So there is a particular velocity induced in bodies because of the expansion of the universe, but they can also have a different transverse component to them because of their mutual gravitational attraction, or it can always have its own particular velocity to begin with. Now, these transverse components of velocities fall off as 1 over a. And as the universe is expanding, these peculiar velocities become very low, and because it becomes very low, you call it as cold. If the velocities were high, you would call it hot, and because the velocities are low, you call it cold. And since most of the matter in the universe consists of dark matter, you call this model as the lambda cold dark matter universe. Now we have measured omega values through various experiments, mostly analysis of CMB data. And we found that the omega for matter is 1/3, omega for lambda is 2/3, and omega for radiation is a very small 10 to the power minus 5. So one thing you can notice here is that when you sum up all these omegas, this is very close to 1. Now, because this is very close to 1, that's how we know that our universe, the one that we live in, is actually flat and it has no curvature. And because the matter part is 1/3 and the lambda part is 2/3, that's how we know that matter, that is everyday matter and dark matter, contributes to 25% of the energy in the universe, and lambda contributes to almost 75% of the energy content in the universe. So 75% energy content in the universe is explained by something that is called dark energy, and we do not fully understand it yet. Now, if you use the same old equations that I mentioned before, you can calculate the age of this universe to be 13.6 gigayears. And this number has not been challenged yet, so we can be pretty confident that LCDM is the right model for our universe. Now we can go on and discuss what happens when we don't make the assumption that the universe has a constant density field. Now we know that the universe has galaxies and galaxy clusters and stars and planets, and all these are little density pockets, and there's gaps between them where there's low density. Now you can see in this picture, which was made by Sloan Digital Sky Survey, each dot here is a galaxy. There are regions which have high density, there are regions which have a low density. So it's not exactly right to assume that the density of the universe is uniform, although it works on large scales. So let's say that we try trying to find out what exactly caused these density variations. So for that, we shall assume that in the very early universe, we had a density field that was constant. And this density field had little perturbations in density that grew as the universe started expanding. Now, as the universe expands, these little particles in the universe, they follow fluid equations because they flow as a fluid. And for that, we can use these fluid equations, which are commonly called as the continuity equation, the Euler equation, and the Poisson equation. Now, you might have seen these in any fluid mechanics course, but if you haven't seen this, you can easily look them up. These are pretty common, and we will follow the same old procedure here of trying to convert these three equations in a co-moving set of coordinates. So when you try to convert it into a co-moving set of coordinates, and you use the fact that there's a parameter delta, which is equal to rho minus rho bar by rho bar. Rho bar here is the average density. So this is actually the perturbation that was there in the very early universe and which later grew and led to the formation of galaxies, because galaxies are nothing but big conglomerations of mass. So you try to plug that into the fluid equations, and what you end up with are these fluid equations for an expanding universe. Now you can see here that the Hubble parameter is playing a role, and the cs square, which is nothing but the speed of the wave in this fluid. And we shall try to solve these equations now for this parameter delta and see how this delta parameter or the perturbation is actually growing in our universe. Now, when you try to solve these for, let's say, a single component universe, so you see that for matter perturbations, you will have a second order differential equation like that, where theta double dot grows like that in terms of the Hubble parameter. And the solution of this we will have two solutions, and one of them will be the growing mode, one of them will be the decaying mode, which we reject. So we use the growing mode here. So the growing mode will grow linearly when it comes to matter perturbations. And when it comes to radiation perturbations, you will have a differential equation like that. And this radiation perturbation actually grows in a sort of exponential manner. But the interesting part here is not this. The interesting part here is that when you take the LCDM model, you see that it initially grows similar to what matter perturbations grow like, but then it starts reducing in its speed. So it starts reducing until it reaches a point where it's almost constant and kind of reaches an asymptotic value. So here you can see this flattening happening here. So in what the conclusion that we can derive here is that in a lambda CDM universe, after a certain point, the perturbations will not grow. And because this perturbation will not grow, you would expect that new structures will not form, because for forming a new structure, you require that this perturbations get stronger and stronger and lead to the formation of these stars and galaxies and whatnot. And because this flattens in a lambda CDM universe, after a certain point, you will not expect any new structure to be forming. This you can see in this simulation that was made by the Virgo collaboration in standard cold dark matter, which is just a fancy name for a matter-only universe. You can see that the little perturbations here are growing and leading to formation of structure. But when it comes to lambda CDM universe, the perturbations initially grow, but after a point, they seem to be slowing down and not increasing further. With that, I would like to stop here, and this was I tried to give you a very basic introduction to what cosmology is and how one can get started in studies in cosmology. And what I would recommend is currently there's a lot of studies going on in astroparticle physics where people try to find out the origins of elementary particles through studies of the very early universe, which comes in astroparticle physics. Now, you must have also heard of something called as inflation. Now, this inflation is just like a hypothesis that the very early universe underwent a small phase of rapid expansion. And why you exactly need this inflation is given by something called as the flatness, the horizon, and monopole problems. So if you can spare some time after the talk, maybe you can go on and Google these things and you will be able to understand why exactly we need a little phase of inflation in the very early universe. Then you can also try to look up what these density perturbations would be like in the nonlinear regime, because these toy models that I have considered here would have linear sort of perturbations, but there are also higher order perturbations that could exist and could lead to more effects that can be probably studied in data that can be collected from these new probes that are being launched. If you are interested in cosmology and if you think that today's talk has motivated you to explore this field a little bit more, then I would recommend that you go and check this textbook by Barbara Ryden called Introduction to Cosmology. This was one of the first textbooks I had studied when I was starting out in cosmology. And the good thing about this textbook is that it starts from scratch and it does not assume any previous knowledge. So I would suggest that this is a very good book to go through. Then there is a book by Steven Weinberg called The First 3 Minutes, A Modern View of the Origin of the Universe. This is a nice light read kind of a book that maybe some of you can enjoy in this period of quarantine. If you're bored and if you do not have anything else to do, you can check this book out. If you have some sort of a background in tensor mathematics or a little bit of knowledge in special relativity, then maybe you can check out this heavy-duty textbook by Gorbunov and Mukhanov called Introduction to the Theory of the Early Universe. This is a pretty heavy textbook, and I would not recommend it unless you have a good background in a lot of mathematical tools and quite some concepts in physics. But it's an interesting book if you would like to seriously study the rigor, with all rigor, what cosmology is about. With that, I would like to end my talk here. I have my email ID here, and if you need to know anything about the University of Bonn or for the fields in cosmology or what it's like studying in Germany, you can always ping me up here. I always try to help, and if you need any general advice, please just feel free to write to me. And that's it. I would like to thank Astro Club for this wonderful opportunity to present this online talk here. And maybe I can take some questions now in the chat. So maybe some of you can type out some questions you have in the chat. Okay, let me go through them one by one. Okay, Pranav here is asking, is there any theory that tells us how dark matter came into existence? Now, dark matter is a little bit of an unsolved question. There are a lot of theories going on right now, people trying to seriously work on what this dark matter thing exactly is, and it has become more of a particle physics problem now than a cosmology problem. So all we can theorize right now is that dark matter came into existence just like regular matter did, but we don't know all of its properties yet. We don't know how it exactly came into existence, but all we know is that it can exert gravitational attraction just like regular matter can. Second question is, can we say that Big Bang, on the other side of the Big Bang is the Big Bounce? So there are some models that can have something like that. Now you can see here that, let me start screen sharing again, just a second. Okay, you can see that in this particular model that we had of the lambda plus curvature universe, you can see that there is a particular bounce that's happening. The universe is actually contracting first. There is a sort of a bounce here, and then the universe starts expanding again. So you could have models that are like that, but the problem is that they don't exactly match with the results that we have from experiment. So the important thing is that any theory you have should always match with experiment. Otherwise, there's no point in the theory if it does not match with experiment. And Ajinkya has a question: do any curvature models of the universe have any observational proof or just theoretical concepts? So the thing is, when you try to explain your models, you have to consider every possibility. You have to consider every possible thing that can happen. All these different models with curvature definitely do exist, but we just proved that these omega parameters explain to us that the universe is actually flat. So we know for sure that the universe does not have a curvature. The universe is actually flat. So you can reject all these models which have a curvature in them. Then Viren has a question. In the Friedman equation, can we take G equals 1? Well, you can take G equals 1 just like I made the assumption of C equals 1. But eventually, when you're trying to convert everything in SI, what we do in theory often is use something called as natural units, where we set H cross and C is equal to 1. And you can, in theory, also do that with G. But you will have to convert when you're trying to express your results in SI. In the equation of state, is there a special condition for radiating matter? Um, well, for matter, you will have the same if you try to look at it from a thermodynamics point of view, definitely when it comes to stars or uh, objects that have very high pressures, the equation of state will not be just P equals omega rho. There will be a more complicated relationship where you will also have the rho square or the rho cube popping up. But the thing is here, because we're considering very large scales, we're considering scales which are higher than megaparsec. So in such scales, you would not take these special points of high pressure into account. So this is a very general model. Again, this does not fully explain our universe, but it's a very good approximation. For specific results like that, you will definitely have to take into account all these special cases. Abhishek has a question. How is omega measured? Oh, that's a good question. So omega is measured using data from CMB. So you try to take all these okay, maybe I should talk about the CMB a little bit. So CMB is the cosmic microwave background, and it is sort of remainder light or the leftover light from the Big Bang. So when the Big Bang happened and it underwent a phase of expansion, whatever, we had like a residual light remaining that you can measure now is the cosmic microwave background. It's in the microwave range. And from this data, you can measure omega, but this is not the only method to do it. There are many more methods. I would suggest that you do your own research for this, and the archive should definitely give you more results. Then Vinesh has a question. Is the expansion of the universe advantageous to us? Well, it definitely is advantageous, considering that if it hadn't happened, we wouldn't be here. I mean, we wouldn't be alive. So the universe in its very early stages had a pretty high energy density, which would have in no way led to the formation of the Earth as it is now. What's your take on Big Bang, Big Freeze, Big Crunch? So I definitely believe in the Big Bang. And going by the lambda CDM model, our universe should go on expanding and expanding, which should lead us to a situation of a big freeze where the universe just expands and the temperature reduces and it goes down to a very low value. And a big crunch would only happen if the universe expands and then starts contracting again. And then we know that this is not going to happen in case of a lambda CDM. So yes, I believe in the Big Bang. I'm positive about the big freeze, and I know, or I'm pretty, it's my opinion that the big crunch will not happen. But you're free to think about these things. It's a good idea to think about these things, why certain things can happen, why certain things cannot happen. So I would suggest that you do your own reading and form your own opinions, and take my opinions with a pinch of salt. So are there any more questions? Okay. Oh, there. I see that there are no more questions. So I would recommend that all of you try to explore this field of cosmology, and maybe this can be one of the fields that you could work on in the future. And with that, I would just like to thank all of Astro Club at Ferguson College for giving me this opportunity to present the basics of cosmology here. And I would like to thank all you people who are helping me with the technical stuff. Thanks for that. And yes, I think, thanks for bearing me. Yes.
Thank you, Apoorva. That was really an amazing lecture, and it's an incredible thing having you here because You're not just an alumna of our college, you were also our senior in Astro Club. And all of our members and our viewers, we thank you for taking your time to give us this lecture. And to everyone watching, we have more lectures coming ahead in Astronomy Week. So stay tuned, stay safe, and we will be back with more. Thank you.